We can't hear you.
Yeah, we can see. Can you hear me? Should I give me to go from here?
Yeah, I think I can take it from here.
Okay.
Yeah, we can hear you.
If I go this way.
I can turn that.
Excellent. So I will start the intro over again, but it's not all that extensive. And I'll also do, we had a couple folks join. Conversation is going to be semi-autobiographical, a little bit of a comments on kind of things that I've seen in my time working in the materials and energy storage businesses. Not necessarily any grand conclusions, but just some trends that I'm seeing. Hopefully we can be interactive on this. So please, at all points, if there's something that either isn't making sense and, oh, is that supposed to be in the middle of that? I believe you, but I'm not sure how I do so.
Grab the top of it.
I have a presentation screen here rather than the actual screen. I've got the PowerPoint presentation screen. I'll keep in the room here. Everybody, graduate students? Do we have any undergraduates? Keep those out of here. None of those. New England folks versus anybody from outside of New England originally. Outside of New England, outside of New England, outside of New England. So we've got a reasonable, like we're about 50-50. I'm originally from Florida, came up here for school, went to Pittsburgh and to Las Vegas, and have been back for 15 years. So I don't know what my characterization is, but it's probably not in New England, but I spent plenty of time around. But as I said, please, let's ask questions in the flow or after. I tend to speak reasonably quickly, so I should be able to catch up. And let's jump into it. You know, this I'm stealing in the title of my talk a phrase, a change on the phrase from DuPont marketing back in the day, better living through chemistry. And it's also been stolen by some other cultural references. I guess there was even a movie using it. But I have bought into my research advisors' arguments and thoughts that all industrial chemistry will become industrial electrochemistry. Pretty convenient from an electrochemist to speak about that. But in essence, that's all leveraging off the thought that the electron is the most efficient and greenest reductant that we have out there. So that's going to underlie most of what I'm going to talk about today, things that I've kind of worked with and working on presently. But I'm happy to be challenged on what's it want me to do for the next one?
Why is it doing it?
So if I just keep clicking there,
Yeah,
like now, okay.
I'll work it now.
Okay. One of our economists, Bob Solo, when I was preparing an earlier version of this talk back in January of 2020, I was reading a alumni magazine, and I ran across this quote, and it really rung true to me, both in my personal experience as well, which is there's a lot of value to innovation, but there's also a lot of value on improving on processes, on ideas, and not being bashful about the fact that, hey, it started over here. And the reason it's really interesting is because we've built on top of an original innovation and done a lot of work. And Solo's noting the point that we don't give enough value often to the incremental improvements and the amount of work and engineering and knowledge that comes into doing the incremental improvements. I'm going to talk about both some very aggressive new innovations, but also a lot of incrementalism in here. So I'll start with where I did my graduate work. I did my graduate work in titanium electrorefining. And some might naturally just start wondering, like, why in the world titanium electrorefining, or what does it amount to? The key reason that we were looking for ultra high purity titanium was for computer chip applications, physical vapor deposition process, where you're putting titanium between aluminum and silicon, because line widths were getting narrow enough. And remember, this is early 90s, so ancient times. But aluminum line widths were getting narrow enough that they couldn't put aluminum directly on silicon, because aluminum and silicon actually don't make a great interface. And so you start to get shorting across. The difference was you put a titanium in between there, and thialuminide and tisilicide have great, nice interfaces. Eventually titanium replaced with tantalum, all of this evolution as you get to finer and finer line widths. But that was the motivation of having a sputtering target, has very high purity, so that when you're in the microelectronics, you aren't getting other pieces in there messing up your communication. So that was the motivation. And in this process, like actually it's a little hard to see in the room here, but this is the product. This product is a titanium crystal. So we're electro-refining it. We're producing something that looks like a Christmas tree. And we're working as a business. We're working all the way across this process. We're working from a sponge plant. Typically, a lot of people make primary titanium coal process. We actually use the sodium processes, a Hunter process instead. And you get a reasonable amount of purification even at that step, because the tickle is reasonably purified. But you get some sponge. We bring it over. We ship it from Utah to Pennsylvania near Pittsburgh. We do fused salt electrolysis. So this is, let's put it in context. This is 8-foot diameter pots, 12, 15 foot tall. Sodium chloride, potassium chloride. We'll go into the electrochemistry of it, but just for scale, you know, we're working at that scale, 30 or 40 of these at the plant. And what we're doing is we're bumping up from 3 nines to anywhere between 4 nines, 5 and 6 nines purity, depending on how the process is running, how good of controls we have on it. Then we take that crystal and we move it into a process that your fearless leader here knows all too well, the e-beam melting of titanium, and produces ingots out the bottom that we're not getting in this process typically too much purification. Usually for these processes from our crystal, quality in is quality out, maybe a little bit of refining at that step. And then the machining and fishing is basically taking an ingot that's about the size of the floor to ceiling here, and slicing it like a piece of salami. You're just making targets. You do a little bit of rolling just to get texture so that we get the sputtering to work the way that we want to work. But pretty much that's like the end-to-end process from raw materials to the product that was sold off into the microelectronics industry. Now, zooming in a little bit on what's happening in the electrochemistry. So this process operates at high temperature because the electrolytes, sodium chloride, potassium chloride, eutectic temperature with a little bit of a superheat. And what happens is you have this pot, and we have this sense of the scale of this pot, and we're dumping in the sponge, and the sponge just looks like little pellets, little rocks, that kind of stuff of titanium, obviously porous, hence the sponge. You dump that into the bottom. You have the salt melted on top. You'd actually have a step where you'd actually chlorinate, you'd sparge, tickle into there in order to get the concentration of titanium in your electrolyte to be where you want it to be. You want it to get to the right ratio. But in its most simple form, the electrorefining process is you're going to oxidize the titanium out of the anode. It's going to transport over to the cathode. You're going to do your reduction there, and you're going to leave. There's a certain number of materials that are rejected into the anode, another set of metals that are rejected into the salt, and there's some that you have problems with, such as iron and aluminum, and they're rejected by never seeing them. They actually saw a difference in purity based on baskets that were used in Salt Lake City collecting the sponge. So just physical contact with the sponge by changing the baskets that were used all the way into the final product coming out as a sputtering target. So there are certain of these things that once they're in, you can't get them out, even with this process. This is the great way for the process to work. The reality of the process is that the average oxidation state of the titanium in these melts in a molten chloride is not 2. It's above 2. And that is because there's a ratio in this between TiCl2 and TiCl3 anytime that you have titanium metal in that same system. There's just the thermodynamic equilibrium between them is such that you mostly have the 2+, but you get some of the 3+. And you're like, okay, fine. You've got some of these pieces along. Why is that an issue? I think folks will immediately see the issue is that you have this redox looping current inefficiency problem that can come out of the fact that you have the 3+ and 2+ option here. You can have some of the 2+ go to the wall instead of the cathode. And it can then get further oxidized. That further oxidized one can then turn back into 2+, and you can have a low current efficiency. Overall, the current efficiency of the system, somewhere in the 60 to 70% range typically. But that was the work of my graduate work, was trying to figure out how we might improve the current efficiency. How might better understanding of what's going on in the melts improve the ability to control this process. So one of the key things to think about is I drew nice little bubbles that are like titanium 2+ or titanium 3+. Those don't actually exist in these melts. They're always complexed. There is a titanium 2+ in the middle there with a bunch of chlorines surrounding it. So it's actually, you're going to see TiCl6, depending on where we end up in the final stage, or we can also see octahedral. I mean, we either have the octahedral, which is the first one, or we can have the tetrahedral coordination. This coordination is the key method by which we're hoping to use at least one of our probes to understand the composition. That probe being looking at the bond lengths between the titanium and the chlorine and seeing how those vibrations are detectable, kind of the same way that people do it in a lot of other pieces. We frankly started off, and I'll give the synopsis here, we started off looking in the wrong direction. We were looking at the Raman spectra that are coming out of that, because that's a very typical way to do a very good job on this. Deeply colored melts, the Raman spectra are very fine-tuned, but they're easy. The excitation is easily lost. So you need to be really close. And with these deeply colored melts, we were losing the Raman signal out. So actually the simpler way, UV vis, actually turned out to be the much more appropriate way in a darkly colored melt in order to look at this composition change. So that's what we did. First, electrochemically, we wanted to see, maybe we could have a probe and see some differences between the ways that you can detect different concentrations of 3+ versus 2+. And so what you're seeing here is you're seeing an AC voltammogram. So we're taking a DC ramp, and then we're putting an AC ripple on top of it, and then we're reading the AC currents. And what that does is that gets some of the thermal noise out of your electrochemistry. But actually, more importantly, and this is what I was pointing here, is, you look at the top, you look at the top scan, and yeah, you can see you're looking at shoulders, you're looking at all these other things. But as soon as you start to get into the AC space, you have other reactions, other measurables that start to become electrochemically important. And so, for instance, if you look at the bottom one, if you look at phase angle, you start to have a phase angle that is a much more peaked response, or as opposed to looking at too many shoulders. If phase angle turns out to be the strongest, easiest response in your voltammetry, then now you have something that also not only is a nice peak, but also is changing with concentration. And those are the two pieces that you're seeing in this rudimentary approach here. So electrochemically, we have an approach that could get, kind of give us something that varies with concentration, and hence they never had a chance practically to characterize their system in operation. They kind of were just looking at inputs and outputs. How did that vary? Kind of, now we have something that can tell you, okay, did your production go up when the concentration changed? How did those production pieces happen? What were the voltage responses in your electrorefining cell? So that was the idea of this PhD work. Likewise, another probe rather than electrochemical probe. Now I've done it. Auto update. Who needs the update? All the way back to the other one. We'll fix that, but I'll keep rolling through. The other probe was the UV vis. The other probe was using UV visible spectroscopy, and once again, sitting at the right the right wavelength and seeing the response depending on the concentration of the species of 2+ versus 3+. We'll pick it up right there, but that was the second probe opportunity. Are we back? Here we go. And once again, we have a couple of different ways that we can go on this, right? We can look at two different approaches, and this is part of what comes here is there's a lot of work in sample prep on this in order to get these chemistries right. And what we're seeing, once again, especially on the bottom one, is we're sitting on a wave number and we're varying the concentration of 3+. And so 3+ is the bad actor. It's the one that we want to look at. We're seeing a response curve, linearize it, that kind of stuff. And we start to see a way for there to be an approach, something that can be in control. Now, this leads me to the two most simple practical outcomes. They never had a reference electrode in their electrorefining cell. And so one of the things this wasn't at all what I was talking about, but one of the things that I had I worked there as an intern, as an undergrad. And so I was doing a lot of practical things, and then they liked what I was doing enough that they thought it would be worth supporting graduate work. What I found was there were a number of ways that you could get a reference electrode into the system, even at an industrial scale. So we're like, hey, let's try to put that in there and see what we can learn. And then the other one was exactly what I just mentioned, the idea that we could use UV visible absorption spectroscopy using fiber optics, put them down into this melt and be able to start to see concentration changes. That's the PhD student just finished their doctorate. Hey, this is what I want to do. Now we get to pragmatism. And one of the things that I wanted to note here is, and I think I actually ran through all of this, but it's really hard. This darkness is hard in here. This cathode may be easier for the folks. Once again, we're in the dark here. So this is the Christmas tree that we're pulling out. And one of the key things I wanted to note for folks is you charge an anode, and then you only pull out a fraction of it before your current goes way down. Like your surface area gets very high and so forth. You only pull out a fraction. So then you pull that out, and there's actually a receiver up top that you evacuate, and you swap in a new cathode. Then you bring that new cathode, and it needs to be, over time, it needs to be longer. So that this distance, as this goes down, this distance comes in. And so you basically have a campaign where you put in a few thousand pounds of anode, and then you're pulling out 100, 200 pounds at a time, swapping out the electrodes. This is about a 72-hour cycle. So this is a long process in order to get this here, 6,000 amps, that kind of a setup. So the reason that's going to become important is understanding where this fits into the whole process. This productivity starts to become a choke point on your overall output from the plant. And this was particularly true right in 2000, as I was finishing my PhD. They were choked. And by that time, the company had been transferred from its startup phase, was owned by Johnson Matthey Metal Company, sold to Allied Signal and Honeywell, went through a merger and so forth. So they wanted to figure out from a corporate way, is there a way for us to increase output without having to put in CapEx, right? Okay, we'll put in a little bit of CapEx. Maybe you have some of these controls. But what actually turned out, and I worked my way through the Six Sigma Black Belt program at Allied Signal, you look at the whole scope and you start to get much more practical again. The best solution, the approach was to look at, this is a 30 production cells over 10, 20 years, all boiled down. Like there's a lot of spread in these data, but this is what it would look at if you were looking at, on this axis is pounds of crystal that came out of the cell. And on this axis is the number of runs, right? So I typically it's like 10, 12, 13 runs in order to get a couple thousand pounds of crystal out. And what happened is you're seeing the productivity. And by the end, your productivity is really bad, right? It's bad, but you need to get it out, because if you leave too much there, then you put the next one on top of it and you're losing all of that material at the bottom that was pretty valuable and you made it yourself. But you look at these data, and these data don't tell you that much about kind of what's going on. It just looks like some variation. And this was where Six Sigma Black Belt, like using your statistical techniques, really came in to help. And the fact that these data, it's kind of three-dimensional compared to what I have here. There's a lot more data behind this synthetic piece. And I actually don't have the source data anymore in order to show all that. But what actually happened is that when you do the SPC, your statistic process control type of experiments, and looking at where your control limits are, where your averages are, across these 30 cells, across the 10, 20 years of work, we found that about the time that you've run 200 runs through a cell, that's the time when you want to refresh everything in that cell. You want to literally dump all the salt out, all of the crud from the anode out, and then you avoid these times where your average is lower and you have more variation. And we did a cost benefit analysis on doing that, and it has a real cost, both in downtime and actual expense of changing the salt and so forth. Basically, we'd get across the plant, we get a $1 million net annual savings just by implementing something as simple as this, because they just basically did it whenever somebody thought that the pots weren't operating well enough. This is the pragmatic aspect of starting to get and understand your system. Doesn't mean that any of the innovation around the probes wouldn't and wasn't effective, but this one was the fastest way to getting some return on the investment. At that time, that's when I actually went into the battery industry. I moved out to Las Vegas and started working in that area. So we didn't get to see through those other two things for my thesis, which was a disappointment, but it was really interesting to run through a Six Sigma process and identifying process controls that can improve the situation. At this point, I'm going to switch to my next topic, but if there are any questions here, feel free to ask and we can ask them later. Now, the next topic, and I may skip through this one rather quickly. Was everyone here? How many folks weren't able to see Dave Bradwell's conversation on the liquid metal battery? Is there anybody here that didn't get to see his talk? Okay, then everybody is fair game for this. Somebody give me a synopsis of what he talked about, just so that I know what he's already covered. The briefest thumbnail. Any volunteers? Somebody give me a primer on what Dave talked about. Anyone? I'm Ferris Bueller's teacher here. Nobody remembers. Okay, well then I'll just dive in. You've sealed your fate now. You had an opportunity for me to skip a bunch. Somebody have a hand? Somebody can do it? Okay. Oh, somebody's volunteering somebody else. That's a good move. That's sort of okay. Then what I'll do is I'll do the most thumbnail sketch, because Dave's presentation will have covered the most important near-term things. I was part of the founding team with Dave and Don Sadaway, getting the business, getting the innovation out into the company. And then since then I went into the deployment side of things. But in its most simple state, and this was actually stuff that Dave did in his second year of graduate school, was making this actual sample that he has here. And you know, it was something that was very appealing, continues to be very appealing, had a lot of recognition. Dave probably didn't notice, but note this, but he was noted in 2011 as part of the Technology Review 35 for that year. So the top 35 under 35. We were very proud of him for that work. The technology itself was also noted the year prior to that as one of the top 10 technologies for that year. We also were lucky enough to have a lot of support for the research on campus from a major energy company, Total, from federal government via RPE, DARPA supported some of the work. The state of Massachusetts helped us tremendously. Even some things around MIT supported the work over a large amount of time. And it was actually the one thing that I'm disappointed I didn't get into this is the picture of the team that we had working at MIT. We grew the group in general up from like 3 or 4 folks to more than 35 folks, but we grew the group on liquid metal battery from Dave to 25 folks just on campus before we even started the company. And really, you probably talked about this. The idea here is, how do you teach an aluminum smelter? So 200 of these cells, kind of going back a couple hundred kiloamp type of system operating 4 to 6 volts. How do you teach this great technology for consuming electricity to give its electricity back? Like that's the fundamental idea of a liquid metal battery. Is we have an industrial example of a very good and efficient consumer of electricity. Can you change the chemistry but use a similar type of approach, because in the aluminum, in the Hall cell, basically you have the aluminum that you make is more dense than the electrolyte. So the aluminum goes to the bottom, the electrolyte floats on top. You actually have a solid electrode as your anode in that situation. So it's slightly different. Liquid metal battery wanted to use all liquid components initially. But that was the key thing. It's like, okay, we'll swap out that solid. We'll use something liquid on that side so that both electrodes are consumed and rebuilt with each cycle. And that's part of what Dave may have showed you, is cycle life is tremendous on this system, because you don't have a way to lose capacity, because you aren't like losing electrical connection piece. That's the problem with lithium ion batteries. You lose electrical connection, so something becomes a dead piece and so forth. Here, you're building both electrodes with each cycle brand new, and you're consuming them and they go away. And that's why it works really well. At that, I'm going to leave it at that. I'm happy to answer any questions. Dave will have done a much better job talking about the business and the evolution of the technology from this initial promise. But what that also led me to do some work in my current development work was looking at the opportunity for grid scale storage, very inexpensive batteries that are very large scale, such as what a liquid metal battery would be, like how they can impact Massachusetts, how they can impact the desires for Massachusetts to achieve more and more renewable energy. And one of the things that we needed to do is, in speaking with both the legislators and the regulators, and thinking about what they'd like to do to see more decarbonization of their system, the thing that requires, there's a disconnect. More renewables are great. It'll help us get rid of the emitting resources. It'll just happen naturally, is an expectation. But they lose the practicality of the way that the grid is managed right now. And what it's managed for, and what's shown on here without going too much into a lot of depth, is I show you this red peak right here. This is in the month of August. So we're doing an 8760 analysis. We're looking at every hour of the year. This happens to be a 2018 type of analysis. We're looking at a bunch of renewables, and we're looking at their impact in reducing the fleet of fossil generators from these renewables. And what happens is you have to keep the fossil generators around for your worst situation. And what that means is that they're trying to get a clean peak. They're trying to get these assets out of there. And on the peak day, you're 90% dirty still. The solution, the idea for this, like where this improves, is if you instead start using battery storage and start creating an asset that's a clean capacity asset that's not fossil generation. And what happens here is I've taken away the split between solar and wind and nuclear and any of those pieces. Just called all of the green generation is here. Everything that exceeds the load is something that we're going to shift with the battery. And are we going to actually make it 100% clean peak with the amount of battery that I'm looking at here? No, we're not. We're getting it from 90% dirty to 65% clean. Like that's the idea here, with just a relatively small amount of batteries. And that's down in the data. That's what your storage gets for you, is it provides you an ability to use the excesses, shift it to these times, and get rid of the dirty generation. Remember kind of this, I'll come back to it a little bit later in another section where we'll give a little bit of a drill down more on that. But in the same spirit of decarbonizing all of the systems that we're working in, there's also decarbonization of processes. And this is one, I think, Adam, did you say Rich Bradshaw had come in the fall? He didn't talk that much about molten oxide electrolysis, just a little bit. This is also some innovation out of the lab that actually has a pragmatic impact. It's the same thesis that I started you with, which is that all industrial chemistry is actually industrial electrochemistry, or should be in the future. And we start with a blast furnace, current way for making iron, virgin iron. And this one's actually in Cleveland, very evolved. It looks kind of dirty, old or whatever, but this is a well-tuned system. This is an evolved system that's highly efficient based on the evolution and the progress that's happened. That's why iron and steel are so cheap. It's a great process, except for the fact that it's using carbon as its reductant. So what if we can take this process, and we're going to do a teaching lesson again, is we're going to teach it to be like this process. We're going to teach it to use electrons as its reductant. And that idea is molten oxide electrolysis. So the idea here is that you're going to dissolve the iron oxide into an electrolyte of oxides. And you're once again, just like the aluminum comes out of the bottom of the Hall cell, we're going to make iron come out of the bottom of this molten oxide electrolysis cell, and we're going to evolve oxygen at the other electrode. And the other electrode in this situation is going to be a solid electrode, and it needs to not be carbon. So in the Hall cell, it's a carbon electrode. And so, it's reasonably clean, even though it's using carbon, because you're not trying to generate oxygen off that electrode, right? That's not what you're trying to do. In this process, we actually are generating oxygen. And if it were a carbon anode on top, you'd be making CO2 or CO, basically you'd be making things that you don't want. So the innovation was to, this doesn't show it. Actually, I think it's more in this stage. The innovation was to find an anode that was inert, it was metallic, and that allowed oxygen evolution at that electrode at a cost that was scalable. This one, it's a bit busy. I mostly provide it just for your reference. This invention from Don and now Professor Alanoy, this is the basis for a company in the area called Boston Metal. This is the way to decarbonize the iron and steel industry. This is primary iron, bulk iron. Every grade of iron can be made from this, and it's a scalable version of a blast furnace. You don't have to build it at blast furnace scale to get the cheapest version of it. They're basically pot lines, just like you can replace. Typically, a blast furnace site might have 3 different blast furnaces. First one needs to be relined. Okay, we'll change that. We'll just add in some molten oxide electrolysis, let the other 2 go. So you can step into this. You don't have to do a wholesale change. But once again, we're trying to come up with innovative ways to be improving processes and improving the footprint. Now, there's also, and I'm going to be even more superficial on this next point, is there is another even more practical approach to improving the carbon footprint of iron and steel making. It's still relying on a blast furnace approach, but instead you're doing some of the processing up front, and it's a process called self-reduction, and you're eliminating some of the operations as the customized feedstock into a blast furnace, the coke, sintering, some of those other pieces that are actually also high carbon footprint steps. And instead you can cold sinter your briquettes of the reductant and the oxide all together. And then what you're having is you're having, instead of this blast furnace and this scale of blast furnace, you instead have a much smaller scale system, very similar to the concept of having a pot line. And once again, this dimension, this is just a slice of it. So once again, you could make this of various scales in and out of it. This type of an approach, we compare that self-reduction process, it's much lower CapEx. It's actually, if you can figure out the business approach for getting a steel company or an iron or blast furnace company to integrate this in, it actually improves their unit economics. One of the big things is those companies are less technologically driven these days than financially driven. Like basically you have accountants running these companies and not metallurgists anymore. So you have a much different, there's very little intuition as to why this should work and how in the decision making into how these could work. It's very hard to get this type of innovation adopted, but it is something that's a very pragmatic, practical thing that could be done as a step between the existing iron production and decarbonization footprint and a world where it's fully decarbonized, maybe via molten oxide electrolysis. Where am I? I got 15 minutes. Let me see if I can run through these last ones in 5 minutes and then leave some time. So the last idea, we're going to come back to another battery, and this is, I have my colleague here, Spencer, who is co-author on a paper They'll be coming out in Nature next month-ish on the aluminum battery. And this is just entirely exploiting the ideas of what is the cheapest bill of materials that I can make for a storage battery. The idea is what's the cheapest metal to use as an anode? Well, iron's the cheapest metal that we can have. Electrically active, not so strong, like it has its limitations there. Aluminum's the second cheapest. So let's try the second cheapest. It's a little bit more electrically active. Cheapest non-metal, sulfur. Sulfur, byproduct of the inherently pretty inexpensive, but also just a waste product from other industries. And how can we get these two to work together as a couple, as a battery that wants to actually store and return electricity? The key thing here is, and this kind of differentiates the battery electrochemists, say, from electrochemists. Battery electrochemists always want to think about the couple. Electrochemists care about the electrolyte. The electrolyte's your enabler for what you can and can't do, because it's the mediator of bad things that happen on either electrode. It tells you how fast you can run. That's the key innovation in this battery, is figuring out a way to have an electrolyte that makes this work. But fundamentally, like, why do you care about it? The idea on this battery and the uniqueness of this battery is that it's so inexpensive that you can actually use 40-hour versions of the battery rather than the 4-hour lithium-ion batteries that you're putting on the electric grid right now. It's 3 to 5 times cheaper, perhaps even more than that, depending on what your total system cost is. And that also, the other interesting thing is the cell size can be much smaller. It's something that looks more like a lithium-ion 18650, like AA C batteries. And what that does for you is, when Dave was talking about the liquid metal battery, like his system size, his smallest system is somewhere, let's say, around a megawatt hour, because his cells are about the size of, this really is going to date me, but the size of a lunchbox. I don't know, do people use lunchboxes anymore? So the old-fashioned lunchbox, like that's his cell size that operates and keeps itself at temperature, because his temperature is up around 300, 400, 500 degrees Celsius. This one operates just above the boiling point of water. So our cell size, our minimum cell size, is about the size of the normal batteries. Why that's particularly interesting, why I'm harping on, is what I have written up here, is now you've got a system that you could deploy 200 kilowatt hours, something that's about the size of a commercial refrigerator. So it actually, for a long duration storage, and there are lots of people, thermal storage, compressed type of things, all kinds of different flow batteries or regenerative fuel cells. A lot of these things, all of them need very large installations. They really don't have a solution that gets you to the right voltage when you're operating in the distribution system, the low voltage system versus the transmission system. When you have a small battery, now when your battery is the same size as the Powerwall battery, you can make a Powerwall system, except for your energy density is a little worse than this, so it's a little bit bigger. That's the idea. You end up with something that looks like a Tesla Powerwall. It costs half as much and it runs 10 times as long. It's a little bit bigger, but that's the idea. I'm going to skip this next piece. That's just talking about why this is a part of the business that's really going. Like, grid storage is really what people need to get to decarbonization. But this is what the battery is about. And this is, you can see the simple approach here. And this is what Spencer worked on at MIT in this somewhat simple approach. And now we're really using a battery that's tremendously inexpensive and actually could work in this form factor. And that's what Avanti is looking to do, is to prove that these small cells, research cells at MIT, can operate and be built in a very similar way to the way that people are making lithium-ion cells in gigafactories all around the world. Like, that's the key. Like, if we can prove that out, then we have a real sense as to where our cost is going to be. Is our cost going to be similar to the range that we project, or potentially a little bit larger because we need custom manufacturing? And I'll stop on this point, but the idea here is that in this 100% renewable scene, and what I was showing you on those data, you need the battery to be so inexpensive that you pay it not to do anything, because you want it there for the literal rainy day. You want it to sit there and be ready when renewables aren't producing the way you want them to. And in order to do that, you can't have it having been run the day before because it was trying to make money. Very expensive batteries need to run as often as possible to get paid as often as possible in the electric system. This is an asset that wants to run less often and get paid a very little bit in order to be there for those days. Thank you, Maya.
Yeah. Okay. Great talk. We're now opening the floor to questions. Just something to mention is that now the microphone of the computer is working, so they will not hear the questions. You might want to
Okay, I'll repeat them if we get some. I may not have inspired folks to ask enough. I kind of failed on learning about Dave Bradwell's talk. Yes, ma'am.
Yeah, it's very interesting talk, and I also work on the battery field. And I have a quick question regarding to the aluminum battery.
Sure.
Like I see you mention a lot of like positive like benefits from this aluminum, like cost and stuff. How about some challenge in the research field nowadays that have like compared to like I also see there is a lithium sulfur battery too.
Yep.
Can you make some like comments on that and also the challenge that they have for the aluminum sulfur battery?
Happy to do so. And for the folks on the Zoom, question was about the aluminum battery and trying to, in one respect, understand what kind of what's different between it and a lithium sulfur system, and just in general, what kind of challenges might this technology? I was very Pollyannish. I talked about just the good things. I would say I'll start with the like challenges. The biggest challenge at this stage is volume of the work. Like there just hasn't been enough work on this particular system done that we can fully characterize the areas where it might have some difficulties. This was one of those technologies that kind of had a COVID curse. The work kind of really just got crunched, and then the postdocs that were working on it went on to other positions, that kind of stuff. Spencer's been all the way through, and he's here with us. So it's really volume of data on enough different systems to understand the challenges. I would say for us, my characterization, our biggest challenge is getting high enough capacity out of our sulfur electrode in order to meet the energy density targets. It's different than the lithium sulfur. And so I'll answer that question. Like one of the key differences is that's where the electrolyte is the key thing here. Everybody that's worked with lithium sulfur is always using electrolytes that are good for transporting lithium. And typically those are organic electrolytes of some sort. And the organics are the ones that start to dissolve the sulfur and cause the redox looping that has problems in lithium sulfur. That's why it doesn't get much cycle life. I won't say that we don't have either the formation of the subsulfides or their dissolution. The data so far indicate that anything that's happening on that front isn't affecting our overall cycle life. So we're getting 900 plus cycles at very high rates. So we're getting cycling that's much better than typical lithium sulfur, but I wouldn't say that we understand it well enough to exactly tell you why. We have some ideas, but more than anything, it's because we're using a totally different electrolyte that probably doesn't interact with sulfur the same way that lithium sulfur. Yeah, it's an inorganic molten salt. So it's a chloroaluminate. There's nothing too tremendously special about it. It's in the Nature paper. We'll have variations on it. But basically that same sodium chloride, potassium chloride that I was talking about in my titanium electrorefining, you add a lot of aluminum chloride to that in order to get it to the right place. And that allows this system to work really well, especially on the charge side. Like that's the impressive thing. When you have a metal electrode battery, you're worried about dendrites. There happens to be a history of work on aluminum electroplating. And bright finishes out of aluminum electroplating, that's the same thing as no dendrites on charge. And so that's the key thing that we're able to kind of stand on top of, that frankly, most battery folks wouldn't look at the aluminum electroplating business because it's more metallurgy than battery type of stuff. But that's the key piece.
All right. So I'm just gonna Hopefully, there's no question in chat. We thank you again for being here.
Perfect.
And thank you so much.
Thank you. Great to meet
Thank
you.
you. Same here.
Cheers.
Yes, I did it.
Oh, you already got it.
Yes.
It's all done.